The galaxy Jade's GN-z11 was discovered by the James Webb Space Telescope in September 2022. Spectroscopic observations by Webb's NIR-SPEC instrument in October confirmed the galaxy's redshift of Z equals to 13.2, which means Webb saw it as it was when the universe was 13.4 billion years old, to a high accuracy. The observation established it as the oldest and most distant spectroscopically confirmed galaxy. However, a paper in April 2023 suggests that the object isn't in fact a galaxy, but a dark star with a mass of around 1 million times that of the Sun. Whether it is a galaxy or a massive star, it's still something further studies will reveal. But up until the discovery of this galaxy, the record holder for the most distant galaxy observed was GN-z11, having appeared only 350 million years after the Big Bang. And now, new observations have revealed that the galaxy contains the most distant and the oldest supermassive black hole in the observable universe. But there is a problem. Using the James Webb Space Telescope, a group of astronomers has identified the farthest and oldest black hole to date, and it is voraciously consuming its host galaxy. Discovering this cosmic giant marks a massive step forward and understanding the mystery behind how supermassive black holes achieve masses millions or billions of times that of the Sun, and that too immediately after the Big Bang. Located within GN-z11, this black hole boasts a mass approximately 6 million times that of the Sun. However, it appears to be consuming matter from the galaxy at a rate 5 times higher than what current theories suggest is sustainable. University of Cambridge Department of Physics and team leader Roberto Maialino described the discovery as a giant leap forward for black hole science. He said, and I quote, "It's very early in the universe to see a black hole that's massive, so we've got to consider other ways they might form. Very early galaxies were extremely gas-rich, so there would have been like a buffet for black holes. Now the size of supermassive black holes that emerged during the universe's first billion years poses a challenge for formation theories. The perplexity lies in the fact that attaining a mass equivalent to millions or billions of times that of the Sun typically needs billions of years of continuous feeding, creating a conundrum for our models. How could supermassive black holes get so massive so quickly? There has to be something wrong. There is a mathematical formula known as the Eddington limit. It's like the speed limit for stars accumulating mass. It's a rule that says a star can only gather mass so quickly before the light gives off pushes that mass away. It's similar to how a car can only go so fast before it encounters resistance, while black holes don't emit light because they're bounded by a light-trapping boundary called an event horizon. Their massive gravitational influence does cause the material that swirls around them to be violently turned and heated, emitting radiation in the process. The more rapidly a black hole feeds, the more intense the light from that region, called an active galactic nucleus, is. Thus, the Eddington limit applies to this region, and it can similarly act to push material away and cut off a black hole's feeding frenzy. But this newly discovered black hole is accreting matter from GN-z11 at a rate 5 times higher than the Eddington limit. While mathematically this can happen only in short and restricted intervals, this black hole is doing it continuously. The team behind this discovery believes that the power of the James Webb Telescope should help uncover more black holes in the early universe. The lead scientist concluded with a fascinating quote, "Before the JWST came online, I thought maybe the universe isn't so interesting when you go beyond what we could see with the Hubble Space Telescope." But that hasn't been the case at all. The universe has been quite generous in what it's showing us. And this is just the beginning. When the James Webb Space Telescope began sending its data, scientists around the world held their breath in excitement because they knew that the observations would challenge the long-held beliefs we held about the cosmos. We know that the Webb observations are divided into different programs, so during one such observation, when scientists were scanning the data that arrived for the uncovered program, 3 very compact yet red blooming objects prominently stood out and caught their eyes. The powerful Webb telescope used the galaxy cluster called Abell 2744 as a foreground lensing body to amplify light from background galaxies, which are otherwise too distant to see. This revealed the extremely red quasar they zeroed in on originally in the form of 3 red dots. In other words, it's just one dot that we see as 3 due to gravitational lensing. Upon more analysis, the object revealed itself as a quasar, and it is seen as it was around 700 million years after the Big Bang. The cloak of thick gas and dust shrouding the black hole indicates its high red shift. But what really caught the astronomy team's attention is the black hole's mass. At around 40 million times the mass of the Sun, it is unexpectedly massive in comparison to the galaxy in which it resides. And that's not all, though. The black hole is surprisingly different from the ones found during that epoch. Yes, you heard that right. Analysis of the object's colors indicated that it was not a typical star-forming galaxy. This further supported the hypothesis that the red dot indeed is a supermassive black hole. Together with its compact size, it became evident this was likely a supermassive black hole, although it was still different from other quasars found at those early times, said the lead scientist of the uncovered program. The finding deepens the puzzle of how supermassive black holes, which can reach millions or even billions of times the mass of the Sun, expanded to such enormous sizes in the early universe. The JWST has now spotted numerous little red dots that are challenging our cosmology like never before. Astronomers have long believed that the supermassive black holes found at the center of galaxies like the Milky Way grew to their current size over billions of years. But the size of this newly discovered black holes suggests that it might be born big, or they can eat matter at a rate that's 5 times higher than had been thought possible and grow quickly. This black hole is essentially eating the equivalent of an entire sun every 5 years. This is actually much higher than what we thought could be feasible for these cosmic monsters. This discovery pushes the origins of this mystery back to black holes' infancy and suggests that the young universe was evolving far faster than we expected. This would overturn the conventional sequence, where galaxies are thought to precede the growth of black holes within them. Instead, primordial black holes would be intricately integrated into the very fabric of the cosmos right from the beginning. However, there is another study done this time by a team of scientists from Oxford, and they politely disagree with the Cambridge department. The Oxford team conducted a detailed analysis of the observations of GN-z11 made by the James Webb Space Telescope. The focus was on investigating alternative scenarios to explain the observed emissions of carbon, neon, and nitrogen in the galaxy central, avoiding the conclusion drawn by the Cambridge group regarding the presence of a growing supermassive black hole. One key aspect of their analysis involves examining the ratio of light emitted by different molecules, specifically nitrogen and oxygen. In the early universe, where only hydrogen and helium were initially present, the first stars formed and fused hydrogen and helium. The heavier elements, including nitrogen and oxygen, will then be produced in the later stages of the star's lives during supernova events. The Oxford team found a notable anomaly in the ratio of nitrogen to oxygen in GN-z11. They reported a 4-fold increase in the nitrogen to oxygen ratio compared to the current ratio observed in the present universe. This unusual abundance raised questions about the processes responsible for the distinct elemental composition of GN-z11. To explain these anomalies, the team explored various scenarios, including tidal disruption events, or TDEs, and runaway stellar collisions. TDEs occur when a star passes too close to a supermassive black hole and is tidally shredded apart, leading to increased emissions. Runaway stellar collisions involve dense clouds of gas forming massive stars, which, due to their proximity, undergo gravitational attraction, causing collisions and subsequent fusion of lighter elements into heavier ones. The Oxford team suggested that these alternative scenarios could potentially account for the observed emissions without necessitating the presence of a growing supermassive black hole. They emphasize the significant uncertainties in the interpretation of the data and refrain from making definitive conclusions about the nature of GN-z11. Basically, the Oxford team's analysis refrains from concluding that there's a growing supermassive black hole in GN-z11. The debate is now wide open, and further observations will reveal which side is right. The universe sure is full of surprises, and we have not even touched the tip of its surface. What do you guys think? Drop in your comments and don't forget to subscribe.